Right, so hi folks, I'm speaking on behalf of the Strong Beams group. We were thinking of trying to figure out a way to read in beam data based on the strength of the beams themselves, because it can sometimes be a little confusing to actually figure out like which beams are actually the strong and which ones are the weak. So we wrote a couple of functions to try and make that a little bit easier for users. And hopefully sometime in the near future, we were hoping to maybe have that work alongside IcePix or other software just to help the downloading process a little more. Since this was primarily a programming effort, there's only going to be a handful of slides, and then I'll also be just working through a couple of notebooks. So it'll also be just kind of short and sweet since we're mostly just going through code. And although my fellow team members aren't here right now, just got to give a big shout out to them because they all did a good job making these notebooks. And we also had some nice conversations on how to generate some ideas. And of course, I have to give a shout out to Jessica, not only for making IcePix, but also just helping us when some of these things were a little confusing. So to start off, as I said, the main idea is just trying to figure out which beams are the strong beams and which are the weak. Because just looking at this diagram, it's not immediately obvious what the strong beams and the weak beams are. Like in a lot of my experiences, the left beams tend to be the strong ones, but then sometimes suddenly you'll see that the right beams are the weak ones. And sometimes you might be really surprised to find that it's one or the other. And I've also, in my own personal experience, I've noticed that some people also get confused by this. So when I try to ask them, sometimes they don't always know either. But fortunately, what we've been working on over the past week is trying to make a couple of functions to make that easier, not just for a singular data product either. We actually made a couple of functions to do this for ATL03, 07, and 08. And so we had some basic case studies working for each of those. The whole idea behind it is that what governs whether or not the designation of strong or weak it's highly dependent on the orientation of ICESat-2 itself. And each of the data products has this hierarchical structure that contains the orientation in this directory right here under the variable sc orient. And depending on that value, that value essentially governs which of your beams will be the strong and the weak ones. If you have an orientation value of 0, then your strong beams will be the left ones, and your weak beams will be the right ones. And then conversely, if you're looking at an orientation of 1, then it's the exact opposite. Sometimes you can also get an orientation value of 2, which refers to the transition phase, which can be a little more chaotic. But that value is also is overall less common. So what you're more likely to find are these two values right here. And we exploited that in order to create our functions and to make it a little easier to identify the strong and the weak beams for each of the data products. So what I'm going to do now is I'm going to go to my Jupyter notebooks in the hub. And we're just going to briefly walk through a couple of case studies. First, looking at the ATL03 data, then we'll look at the 07 and then the 08. So kind of like what we've been doing for each of our tutorials, we obviously have to bring in all of our imports. In order to actually look at the data, we're going to use both IcePix and S3FS to get data from the cloud. And in this case, Eric specified some some query objects with this spatial extent and looking at November 30th. So we run this query object and we check what granules we have available, both normally and in the cloud. And we see that we have a fair number, that we do have a few data files that we can work with. So we can start the process to get all of this data downloaded. Might take a little while. There we go, perfect. And then we can run through all of these and then finally load up the files from the cloud itself. And it's quite nifty to do it this way because through this, we have our data file without actually downloading it into the cloud, into the Jupyter Hub. And so now here's the function itself. The main idea is that we are going to, depending on the orientation, which we load using this line right here, we can define the configure, sorry, let me rewind. Based on the orientation and using an input known as strength, we can determine which are the strong and the weak beams. And then we can pull out the data as we want. This was actually an unsuccess. This was one previous attempt from Eric to get this to work. So he and I worked together to write another one that's a little more in depth. So the whole idea is that you take in your data file and then you specify whether you want the strong or the weak data. And based on that, it'll take the strength, whatever strength you choose, and then feed the corresponding data into a bunch of data frames. So in this case, if we want the strong beams, then it'll put like the strong left, the strong central beam, and the strong right beam into their own data frames. So if I do all of this, and then so I have the function activated, and now I'm going to specify that I want only the strong beams for the file that we downloaded from the cloud. This will probably take a moment just because ATL03 is a very large data set. But while that's running, I'll just mention what's going on in this last cell. For this last cell, we're pretty much just plotting the data just to make sure that it looks good. I've also applied a little filter using the signal confidence variable. So we're only going to be looking at high confidence photons, which means we're most likely only going to be looking at what are signal photons over this region. So if I run this, and wait for a little bit, wait for a long bit. There we go. We now have these three plots that show what the data looks like for each of the beams. And as we can see over this region that Eric was looking at, they look pretty similar. There is some weirdness going on right in this region that seems to differ between the two locations. So that might indicate that there's some variable terrain in this region. So that's how it works, simply works in the ATL03 data. Now we can look at it with ATL07. And this one was constructed by Ming, so props to him. He followed a similar process to what Eric did in that he constructed the functions based on the orientation and whether or not you want the strong beams or the weak beams. So I'm mostly going to glide through this since it's the same general idea. And as we can see, just like with the ATL03 plots and data, we're going to put all of these into data frames. And something else that I glossed over, but since the transition phase can be a little weird, just to keep things simple, we're passing off an error if there's a transition phase going on within the data file. So I'm going to go through all of these. Here we have an ATL07 file that is being used as input into the functions. And we can indeed see that the orbit info structure is within this H5 file. So that means we can identify what the orientation means. And then we feed that into the functions. And we can see here that we have the strong beam data. And conversely, we can do the same, but for the weak beam data. And so using this function, we can plot the data as we want. So here we have a basic plot of sea ice elevation for the weak beam. And then here it is again, but for the strong beam. And as is noted here, there was some odd filler data at the very beginning. So we can do a quick bit of slicing to get rid of that and exclude that data, and we get something that looks like this, which looks a lot better. And again, it looks fairly similar to the weak beam data, but you can see some localized differences, particularly right here at the end of the track, which means that once again, we're looking at some pretty coarse, it looks like we might be looking at some pretty coarse ice. Then lastly, just to look at some ATL08 data using, once again, we're going to do the same thing. This is the same function that was applied for Eric and Ming's notebooks. And then what we're going to do next is call in the data using IcePix. I'm specifying some variables here to look over the Upper Peninsula of Michigan, just as like a personal thing. I really like the Upper Peninsula. And so then we put in our granule order. Hopefully it doesn't take too long. And thankfully it did not. And now we can download those granules. And like the previous notebooks, we can use the function to extract our strong beam data. And it's very quick, which is very good. So now I have this cell here just to take a look and make sure that all this data is there, and it's over the Michigan UP area. And it sort of is. It's kind of closer to Thunder Bay in Canada, but it's where I wanted it to be, and it actually subset to where I wanted it to be. So this is good. And so that means we can plot this. We can plot the strong beam data, and here's the plot for looking at the strong beams. And you can see that for what little canopy it's actually detecting, it varies quite a bit between the three beams, which is very interesting. I actually don't know a whole lot of how ATL08 works, but it is interesting to see just such drastic differences over such a small spatial scale. All right, so that was the three notebooks that I wanted to go through. And I feel, and through that, we were able to show that, that this function does a pretty good job at separating the strong and the weak beams. So what we were thinking about doing was trying to potentially add beam as a potential query input into IcePix. So as one of the inputs, such as spatial extent and dataset and RGT. But just through discussions with each other and with Jessica, we did find out that it would be a very complex and daunting task to do this. It is in theory possible, but we would have to do a little more. We would have to do a lot more, I should say, in order to get it properly implemented. So at least in the near future, it might be easier to have it work alongside IcePix or other software rather than be fully implemented. So that's basically the gist of what we did over the past week. In terms of what could be done next, so far we've only looked at it for the ATL03, 07, and 08 products, but it would be also cool to try and apply this to some of the other products, just to give a little more flexibility. Even though the linkage with IcePix might be difficult, it would still be cool to get that in there. Then maybe also getting some basic statistics between strong and weak might be a neat little thing to add. And then we were also speculating on some possible customization options, like whether or not to put it into pandas or X-array, looking at like allowing users to specify whether or not they just want the strong beams or the weak beams, or if they just want to look at a single beam as opposed to all of the beams of one strength. So yeah, there is a lot more that we could do with this, but this is what we were able to do this week. So I just want to once again thank my fellow group mates, and yeah, we can take any questions. Otherwise, thank you.